Planet Terra, our home. Nature, tranquility, our way of life. But Mother Nature is an untamed mistress.
Sweet geology! No!
Look familiar? Geohazards like these are happening all over the globe right now. And you could be next. That is, unless you decide to use remote sensing.
So, if you haven't gathered from the introduction, this video discusses the application of remote sensing in geohazards. But before we begin, let's quickly delve into the definition and history of remote sensing. My favorite definition comes from Blilsand et al., who define it as the science and art of obtaining information about an object, area, or phenomenon through the analysis of data acquired by a device that is not in direct contact with an object, area, or phenomenon under investigation. So in simpler terms, it's observing from afar. Most scientists and historians agree that remote sensing finds its origins with the advent of photography, with most people associating remote sensing with aerial photographs and satellite imagery. In 1858, a man named Gaspard Villiers-Tournachon used a camera strapped to a balloon to take the first aerial photograph over Paris. Sadly, this photo has been lost to time. However, 2 years later, James Wallace Black copied this idea and took an aerial photograph over Boston, which is the image you see on screen. Wait, Boston? I heard they love tea parties. Jumping forward in time, remote sensing achieved major milestones during the 30s
to 40s, ladies and gentlemen, where we started harnessing the power of the electromagnetic spectrum, in particular radio waves and radar technology, to its full capacity, replacing the giant acoustic horn and aircraft detection capabilities. In addition, we started seeing the widespread use of sonar. These two systems work in a very similar fashion, relying on an emitted pulse of energy reflecting off an object, where calculations are run to determine distance based on time of emission to time of reception.
Well, that's kind of the shorthand explanation, mysterious radio guy. Moving on, the next major milestones we saw came along with a more in-depth understanding of the electromagnetic spectrum, where color infrared films, which, you guessed it, sensitive to long-wave infrared lights, was used in identifying diseased plants. This later laid the foundations during the 60s and onwards, where major advancements in remote sensing occurred, being formalized as a science after the launch of the TIROS-1 satellite, the first meteorological satellite in 1960. Followed by Landsat-1 in 1972, which ultimately led to hyperspectral remote sensing in the 80s, which allowed satellites being able to sense over 200 defined spectral regions along the electromagnetic spectrum. Yes, I am aware that I have mostly spoken about satellites and photographs, and there are hundreds of more types of remote sensing, and by this point you may be wondering how remote sensing plays a role in geohazards. And we will get to that. But first, let me explain a few more things. By now, you all should have a rundown on the history of remote sensing. It is also important to understand there are two types of remote sensing, active and passive, with active remote sensing devices requiring an induced signal to be generated, which then relies on measuring that signal's reflection and its properties. Examples obviously include radar that induces radio waves that gets reflected back to the device and is measured, whereas passive remote sensing skips this inducing process and relies upon an external source for its signal. Most often this would be the sun. This is how the Landsat satellites work. It measures electromagnetic radiation reflecting from the Earth originating from the sun. But it is important to note that we are not limited to the sun as an inducing signal. Earthquakes, conventional radiation, and many other objects or events can act as a source that allow for passive remote sensing to take place. Now, we also need to understand that remote sensing takes the form and gets attached to many types of systems and devices. We already know about satellites orbiting the Earth. We also get geostationary satellites and ground-based systems, stationary and dynamic remote sensing systems, aerial types such as drones and aircraft, vehicle-mounted systems such as the Google Streetcar. Basically, these systems include whatever you can mount a sensing device to. Finally, we have reached the point in the video where we talk about remote sensing in geohazards is an invaluable tool. Geohazards are seen as environmental conditions that pose a risk to the safety of human life and property. These hazards are often rapid and triggered by Earth processes. They include geological hazards such as earthquakes or volcanic eruptions, climatic hazards including droughts, cyclones, even biological hazards such as locust swarm. Remote sensing can be and is used throughout all spheres of geohazards to monitor, sense, predict, and manage geohazards with the focus on limiting the impacts they have on human lives. I like to mention Japan when talking about remote sensing in geohazards, a country known for its many tsunamis and earthquakes, where, starting in the 40s, no radio guy this time?
Japan introduced tsunami warning systems along the Sanriku coastal area. Using an array of seismographs, the Japanese used triangulation to calculate and determine the epicenter of the quake, and depending on the magnitude, determine the size and severity of the tsunami. This technology later evolved into the modern-day ocean floor nervous system, allegedly covering every square inch of earthquake-triggering faults the country has, with sensors being able to detect even the slightest signs of earthquakes and tsunamis, allowing for automated warnings to be sent out up to 20 seconds before the earthquake occurs.
This guy. Well, yes, Japan does have a long history of using remote sensing and seismographs to detect earthquakes. But not only is remote sensing used to detect incoming hazards, it is also used to study the aftermath, such as the Interferometric Synthetic Aperture Radar Satellite, or INSAR for short, which measures the ground deformation using a process called interferometry, which combines radar images taken before and after an event, which shows even the slightest and most subtle elevation changes, down to the millimeter. This satellite is used in detecting and monitoring surface elevation changes, mud and rock slides, volcanoes, and coastal erosion because of its ability to measure large surface areas instead of a few points. It also has the added benefit of not subjecting field crew to dangerous and hazardous conditions, a running theme with remote sensing in geohazards. Okay, so what about desertification, rising sea levels, plant diseases, and all these other geohazards? How does remote sensing play a part in all of this? Well, the type of remote sensing is dependent on the type of geohazard. Most commonly, we look at past and current satellite images to examine and determine the rate of change. This is common for desertification, coastal erosion, and many other geohazards. Plants, for example, reflect solar radiation differently depending on their conditions. Each object on Earth has a spectral signature, meaning they exhibit different properties of spectral reflection. In simpler terms, they absorb specific wavelengths on the electromagnetic spectrum and reflect unabsorbed wavelengths back. A stressed plant may not readily produce chlorophyll, resulting in a decrease in red and blue band wavelengths absorption. This alters its spectral signature. With these signatures, we can then identify plant types, cover, health, even water retention and droughts. With all of this data that we collect from remote sensing, we can then implement this into a GIS system where we can visually present and model geohazards, their extent and severity, and use this for risk assessments, early warning systems, rehabilitation plans, disaster response contingencies, and so much more. Finally, the reality is that there are hundreds of applications for remote sensing in geohazards, and a 10-minute video is too short to discuss them all, and I am more than willing and happy to answer any questions outside of this video for you. With that said, I hope that you were at least able to learn something from my video. Thank you very much and have a lovely day.